In this video, I want to show you why divergent series in mathematics, but especially in physics, they are used in physics quite a lot. In quantum field theory, for example, they are very useful because even though they technically diverge, if we truncate the series to a certain point, we still find meaningful results. And I want to show you this by means of a simple example. We start from a function that I define as a function of a parameter that I call t, and I define it as an integral of the following form, integral from 0 to infinity. Then we have the exponential of minus x squared minus t, x to the power 4, dx. So integrals of this kind, now I will not get into the details, but if integrals of this kind arise, for example, by considering path integrals in quantum field theories, we might have a theory with a certain interaction term of this kind, and this parameter t is related to the interaction. In this case, this is a self-interaction because we only have one field. If you think of that in this way, so x is related to the field, whatever that is, because I'm not really getting into the details of that, and you have to study some quantum field theory, in particular quantum field theory with the language of path integrals to get more insights, some physical insights related to this. But we take this as a starting point, so we want to find something meaningful by calculating this integral. And the problem is that this integral here cannot be computed really in a well organized and a well written closed form because of this term in the integral. So if, for example, we set t equal to 0, this term disappears and you simply have a Gaussian integral that can be evaluated. But more often than not, in any meaningful physical theory, you have these integrals that cannot really be computed in a closed form. So one way to tackle the problem is to expand this exponential with respect to the variable t, then you find a series, and by switching the order between the integral and the series, which, by the way, cannot always be done because you might give rise to divergences, and we will show that. But even by generating such divergences, I want to show you that it is actually useful. Now you can see that if this parameter t is greater than 0, this integral here does not diverge, because you can see that we have these minus signs, so this exponential decays, and even when you integrate over large values of x, when we approach infinity, we still get quantities that are very close to 0, and therefore this integral converges. Now, let's do what I said earlier. We want to expand this exponential with respect to t, so we can rewrite it in another way, like this, integral from 0 to infinity. Then you have something of the following kind. You have e to the minus x squared, which you can factor out of the summation, and then you have an expansion over n from 0 to infinity of the following form, minus t to the power n over n factorial, and then you also have x to the power 4n dx. Now, this equality here still holds because we have simply expanded the exponential, but we have not changed the order between the series and the integral. And that's when problems arise, especially when you think that you can make your calculation simpler by doing this, you might generate some divergences. So if we swap the order between the sum and the integral, we cannot really put an equal sign because I will show you that we get a divergent series. So the equality does not hold, but physicists use the following symbol, which means that we get something asymptotic to a series. So our function f of t is asymptotic to the series that I'm going to write, and I will explain technically what this means in a moment. First, let me write the series like this. So we simply put this summation outside of the integral, and we can write it in the following way: minus t to the power n over n factorial, and then we have an integral from 0 to infinity e to the minus x squared times x to the 4n dx. Now, before explaining this symbol, as I said, I want to rewrite this integral here. That integral can be written in terms of the gamma function. In particular, the gamma function of a variable z can be written as an integral from 0 to infinity e to the minus, let's call the variable of integration t to the power z minus 1 dt. So this t here is not the same as this t here. But anyway, so this is an integral, and this integral holds for the real part of z greater than 0, otherwise you get a divergence there. But this is not really interesting here. Now, the integral that you see here can be written in terms of the gamma function. In particular, let's rewrite the integral from 0 to infinity e to the minus x squared x to the power 4n dx. Let me rewrite it in the following fashion. So I will rewrite this dx as d of x squared divided by 2 times 1 over x. So the differential of x squared is just 2x dx. So when we divide by x times 2, this is equal to dx. So this is just a mathematical trick. Integral from 0 to infinity e to the minus x squared. Then let's rewrite x to the power 4n as x squared to the power 2n. So when we divide by x, we can rewrite x as x squared under the square root, so x squared to the power 1/2, because we know that x is non-negative since we are integrating from 0 to infinity. So it's not a problem for us to square it and to take the square root, because we get a non-negative number by doing this operation here. So we are not doing anything wrong. We can do that in this case. So I can put a minus 1/2 here, and then I simply have dx squared divided by 2, so I can put a factor of 1/2 here. Now we can rewrite this 2n minus 1/2 simply as 2n plus 1/2 minus 1. It's just a trick. But by doing so, you can see that I have written the integral in exactly the same form, as you see here for the gamma function. So this will give us 1/2 gamma function of 2n plus 1/2. So you see the argument of the gamma function from here. And therefore, you can rewrite the series like this: summation over n from 0 to infinity, and then we have the gamma function of 2n plus 1/2 divided by 2 times n factorial times minus t to the power n. Now, if you try to compute this object here, and I have used, for example, Wolfram alpha, so you can simply consider a function of the kind gamma of 2, then you choose a value of a number. For example, you can choose 70 or whatever. Treat this as an integer, and then you set plus 1/2, and you divide by 2 times 70 factorial, and you can calculate this. And you can do that for every value of n. And you see that as you increase n, this ratio here increases. So this object will explode as n becomes larger and larger, which means that the series will converge only if t is equal to 0, because otherwise we have no convergence. These terms explode. So this is a simple way to see that when you exchange the order between the series and the integral, well, you have to be careful, because you can create divergences, and therefore the series will not be equal to the initial integral, which you see is, the integral converges for t greater than 0, for every value of t greater than 0, but the series does not converge for this range of values. It converges only if t is equal to 0. So, you can see that Apparently, there is nothing meaningful about what we did. But actually, this is more meaningful than it seems. And this is exactly what happens in physics. When you have divergent series and you try to make meaning out of them. First, before proceeding further from here, I want to tell you what physicists and even mathematicians actually mean by putting this symbol here. As I said earlier, that symbol means asymptotic. So what does it mean that a series is asymptotic to a function? So let's consider the following series, summation over n from 0 to infinity, a sub n, x to the power n, so we can call this f of x. This is a function of x, as you can see here. And we want to consider now a truncated version of this series, so summation over n from 0 to capital M, which might be finite, a sub n, x to the power n. So we say that this series here is asymptotic to this function if we consider the absolute value of f of x minus the function summation over n from 0 to m a sub n x to the power n. This must be less than epsilon x to the power m. And you have to think that m and epsilon are given, and this result holds for those values of x which are smaller than a certain xi. Let's call it xi. So this is a technical definition for asymptotic series. You can see that if we consider x large enough and m large enough, in particular if you let this go to infinity, you see that this term will explode for x large enough, let's say, even if that's not really proper terminology. But you see that the difference between these functions can even be an infinite number. Whereas when you talk about convergence, here on the right, you don't have something that depends on x. You have something that is proportional to epsilon, let's say. So convergence is a different definition. This is related to the asymptotics of functions. And that's why I have considered this symbol here to denote the fact that we don't have an equality, but rather the function is equal. If you want to consider an equality, you have the function equal to this, plus you have a discrepancy. And the discrepancy tells me that the two functions are not at all the same. But anyway, now that we have this expression, let me show you that actually even divergent series are useful to evaluate non-divergent integrals. So remember that we started from a non-divergent integral for t greater than 0, and here we have found a divergent series. But now let's evaluate the first few terms of this expression. So let's call this term g of t. Let's evaluate the first few terms, g of t. Now you can evaluate the first few terms of this gamma function, for example, by resorting to Wolfram alpha. And the first few terms gives us the following for g of t. So we get a factor of square root of pi, which comes from this gamma of 2m plus 1/2. So basically, when you want to evaluate, for example, the first term, here you have to evaluate gamma of 1/2 for n equal to 0. So 0 factorial will give us 1, and gamma of 1/2 is equal to square root of pi. So we get a square root of pi, and then of course here we're left with 1/2. And then we have the other terms. When n is equal to 1, you can see that here we will get minus 3 over 8 times t, and you still get this factor of square root of pi. Then you get plus 105 divided by 64 times t squared, then you get minus 3465 divided by 256 times t to the third. And then you get, of course, higher order terms, but we will truncate the series to third order. Now you can do the calculation when t is equal to 1 over 50, for example. So we choose a small number which is still close to 0, because remember that the actual convergence of this series is when t is equal to 0. But now let's see what happens if we truncate the series and we calculate it when t is small, so close to 0, but positive, and we get that this is approximately 0.8739. So I'm talking about these terms, these four terms, and it will give us this result. If you do the same with the integral here, you get something very, very close to what we found just now. So you have to set t equal to 1 over 50, and you can see by doing numerical integration there, for example, you can do this, you can calculate this in Wolfram alpha, and that's what I've done. You can see that this g of 1 over 50 is also approximately equal to f of 1 over 50, which is our initial integral. And this shows you, I mean, just intuitively at least, that even divergent series, which appear actually very often in quantum field theory, for example, in physics, are very useful because they give us a lot of information regarding the physics behind the theory that we are considering. So this is just some hints that I wanted to give you.